So this time we want to look at doing a substitution of tan of theta on 2. So going back to our t formulas to do some questions. And usually these ones are in this form. dx over a cos x plus b sine x plus c. Not easy. Not easy. That looks ugly to start off with. And then we're going to do a substitution for tan of theta on 2 for these ones. So what do we got to remember? From our extension 1 course, sine theta is equal to 2t on 1 plus t squared, cos theta is 1 minus t squared on 1 plus t squared, and tan theta is equal to 2t on 1 minus t squared. We've got to remember those relationships to solve and do the manipulation here, because we've got to do looking at the type of question here that and the manipulation that takes place it's a bit intricate. So we get the substitution of tan of x on 2 for t to solve dx over 1 plus cos x minus sine x. Now we do dt, that derivative of tan of x on 2 gives the half sec squared x on 2. Now where does sec x on 2 come from? Well, obviously it comes from the idea of cos of x on 2. Now where does x on 2? Well, if tan of x on 2 is t on 1, then by Pythagoras' theorem we get the square root of t squared plus 1. So cosine would be 1 on t squared plus 1. So sec then would be square root of t squared plus 1 over 1. So that's where we get the half outside of 1 plus t squared dx. Now notice it's dx with t here, so we have to divide by 1 plus t squared multiplied by 2. So that's where dx is equal to 2 plus 1 plus t squared dt. Told you it wasn't easy. And that's just getting dx in terms of t and dt. Next step is to do some substitution of the other ones. Now, again, we remember our relationships here, because we're getting 1 plus cos x t minus sine x. So we replaced dx there with 2 on 1 plus t squared dt. And then we've got the 1, well that didn't change. We've got the 1 minus t squared on 1 plus t squared, which is the cos theta, and sine theta is 2t on 1 plus t squared. So let's start off with. Now we've got to clean this up a bit. Let's get a common denominator for our big denominator here. So we get 1 plus t squared on 1 plus t squared. The others are okay, we don't need manipulation. That will get a cancelling of t squareds there. Cleans it up a little bit. The 2 plus 1 plus 2 over 1 plus t squared over 2 outside of 1 minus t over 1 plus t squared. Oh, that cancels. The 2's will cancel. That gives us dt on 1 minus t on 1 minus t, which would give us natural log of 1 minus t plus the constant, which is natural log of 1 minus tan of x on 2 plus the constant. Wow, there's our answer there. So you can see how once we got in there, it started to clean up rather nicely, but it's a bit of work involved. But that's the way we've got to do these types of questions. This time we got 1 over 1 plus cos x plus sine x. So t is 10 on x on 2. So again, dt is half sec squared x on 2 dx, which we can do that substitution and get a half 1 plus t squared. So that should be a dx there. And then the dx becomes 2 on 1 plus t squared dt. We know what cos and sine of x can be, what they can be written as, so we do our substitution for that. And so again, we start to clean it up. We have to get our common denominator again. We cancel our terms that we can, and we get 2 plus 2t. So that starts to clean up there. Then we get down to this one. We get the dt over 1 plus t squared. So always check the algebra carefully with these. Natural log of 1 plus t plus the constant. And then, well, t was tan of x on 2. So that's where what it comes out to be. This time we've got cosec theta to theta, and we want to do that as using t equals tan of theta on 2. Well, remember cosec's 1 on sine, so again, get the theta as the 2 over 1 plus t squared to t. And so if sine is the 2t on 1 plus t squared, then we can put cosec as 1 plus t squared on 2t. Now when you do this one, we've placed the theta, replaced cosec. We got nice things start to happen here, because that we get a cancelling there. The 2 cancels. Leaves us with dt over t. So that gives us natural log of c, and natural log would be tan of theta on 2. Beautiful. So when we start to see that type of situation, it doesn't seem like it's too hard, but you're not going to be able to go straight from there to there. So you don't have your table standard integrals doing that for you, but that's where it starts to come into play. So this time we got sine of x on 2 plus cos of x using tan of x on 2. So again, we can get our dt it's the 2 dt over 1 plus t squared. Sine of x is 2t over 1 plus t squared. Cos of x is 1 minus t squared on 1 plus t squared. So we start to clean it up. We get a common denominator here. We multiply this one, we get the 1 plus t squared. And then we clean up this one here, 2 times 1 plus the 1 is, and the 2t squared minus t squared. So where 3 plus t squared comes in there. The 1 plus t squared's cancelled with the square there, so that's why it's just 1 plus t squared there with the 4t. And so we get 4t over 1 plus t squared, all divided by 3 plus t squared. Starts to look like that. Now, when we look at that expression, well, how are we going to do that? Let's do some partial fractions. Time to do some partial fractions, because that's what it comes out as. So we have a look at the partial fractions. With 4t would be the at plus b on the 1 plus t squared, and we get the ct plus d on 3 plus t squared. So get our numerators, equate them, and then start to solve. We end up with b and d being 0, and we get a is 2, c is minus 2. So that starts to be nice there. So there's 2t on 1 plus t squared, which gives us a log function nicely. 2t on 3 plus t squared, again another nice log function, and then do our substitution of t back to tan of x on 2, and we get our expression there very nicely. Question 5, we got 1 over 5 plus cos x, where t is tan of x on 2. Now this time we've got to do our substitution of the 2 pi and 3 and 0 as well, so there in the blue is those substitutions. That's why the 0, the 2 pi and 3 becomes 0 to root 3. Cos x is the 1 minus t squared on 1 plus t squared. Dx becomes 2 dt, 1 plus t squared. We've done that every time, so that starts to become a bit of a standard result as such. Again, cleaning up the denominator, this part here, that denominator, multiplying through, getting a common denominator, and you get the 5 over 5 plus 5t squared plus 4 minus 4t squared. So we start to be able to clean it up to get 2 on 9 plus t squared. No t up the top, so it becomes an inverse tan function. And then we can do our substitution. We don't have to go back to being in terms of x, because we've done our substitution for our values there. Put root 3 in, put 0 in, and you're able to do the calculations to get it all down to pi on 9. So there's some questions using the t substitution. So have a look and be wary where you can use this. A lot of times you'll be told to use the t substitution, so it's not too bad. But again, it probably doesn't have to be given to you. So you have to be wary where you can see. So look at the types of function we've seen, and be able to see those ones when they come up, and be able to use a t function if necessary to solve the problem.